warm welcome to everybody, each one of you, ladies and gentlemen, boys and girls. We'll start with the program. We have our guest over Dais, and we would like to welcome everybody to the event. This is a one-day event organized by the Chemical Engineering Division of the Institution of Engineers. So the Institution of Engineers in itself is a legacy of more than 100 years of professional body of engineers, and they have contributed to the development of the nation time and again. And it is a very old institution. Maybe the current generation would not have such a connect with such an old institution. And the basic purpose of doing such programs is to connect with the youth with the legacy. So the youth should appreciate the legacy and take it forward in its journey. So we would always encourage the youth to become the member of Institution of Engineers and shape the industrial and the technological infrastructure in the country. So whatever the membership of the Institution of Engineers, it opens up the professional practice of engineers, and it gives you a connect to the large diverse field of engineering. All domains of engineering are covered in the Institution of Engineers, and particularly I am from the Chemical Engineering Division. So I would have connected with many of you. My name is Abhik Tushar Das, and I have tried to help organize this event, the one-day event of the Chemical Engineering Division. And we have tried to connect with the industry and the academia, and I hope the members who are present over here would take something back with them, and it would definitely be an encouraging fact to see you all grow and take the vision of Viksit Bharat of India 2047 when we complete 100 years of independence. So we wish to be a developed nation by then. So for doing that, it would need participation from each one of you. Just to talk about the Institution of Engineers, we have 27 state centers in the country and 94 local centers. So the Vadodara center is a local center and the state center is in Ahmedabad. So and we have also 4 overseas chapters abroad. Here in the Vadodara local center, we actively try to bring out programs on maybe 2 in a month. We try to make programs and lectures sessions. So it would be very encouraging for us if you can join each event. We do have your communication mobile number and email address, and we will keep sending you the invites. Everybody doesn't have so much time to attend each and every program, but yes, definitely your participation would definitely help create this infrastructure of engineers and the talent pool, and it will take the your career also in the country also forward. And most importantly, it gives you a voice. The engineering committee should have a voice, and that voice needs to be felt only when it is united on a platform. So the Institution of Engineers gives you a platform to bring out your talent, your nascent ideas. You may have so many ideas, but to bring out it on a platform where you connect to the engineers across the country, that the Institution of Engineers can provide you, and it is then up to you how best you can utilize this. So the what is the importance of chemical engineering? I think all of us maybe primarily are chemical engineers, so and engineers know the chemical engineers are specialized in. I work in fertilizers, so yes, fertilizers, petrochemicals, refining, oil and gas, pharmaceuticals, polymers and plastics, environment, and waste management, metallurgy, and emerging sectors like green energy. So these are all facets of chemical engineering, and have just 4 topics today to deep dive into some of the aspects. Maybe we cannot cover everything in one day, but we will try to touch upon basic aspects of chemical engineering that may help you to ignite some ideas in your mind, which may take that idea forward and maybe be successful in here. The chemical sector contributes around 7% to India's GDP. That's quite a significant number. So, chemical engineers are one of the basic engineering fields in engineering, and definitely they have a role to play not only in the sustainable future but also to create value for the country. Yes. So, not taking much of your time, I'll ask Deepak sir to come over here and address the August gathering. I hope you enjoy the session. Thank you.
Good morning, friends. Welcome to Institute of Engineers, Baroda chapter. We have Mr. B.N. Kolkapur as a chief guest today. Our chairman, Shri Kirubhai Thakur. The first session speaker, Shri Yagnik sir. The second session speaker, Shri Jansari sir. Third session speaker, H.P. Pandya sir. And the last session, Someshwar Vyasarji. So he will come in the afternoon. So let's do a small formality and prayer Vanda, Ganesh Vanda. ગણેશજીને વંદના કરીએ કે કોઈ વિઘ્ન આવે નહીં, તો આપણે અહીંયા ક્યાં વિઘ્ન આવે? આમાં વિઘ્ન કેવું આવે? કોઈકની રિંગટોન વાગે, લંચ પછી લોકો ભાગી જાય, તો એ વિઘ્ન ના આવે એવી આપણે ગણેશજીને પ્રાર્થના કરીએ. With this I request all the guests to join for the deep prayer. So now I request our chairman, Shri Kirubhai, to give the welcome address. Thank you.
Good morning, everyone. Respected Sri Mankapur sir, other eminent speakers of the day, my colleagues from IIM Baroda, budding engineers. I am very happy to see all budding engineers here today. Ladies and gentlemen, on behalf of Institution of Engineers India Baroda Local Center, I extend warm welcome to all the dignitaries on and off the dais and to each one of you present here. I am delighted to inaugurate this full-day workshop on emerging trends and operational excellence in chemical engineering. Before we commence, I would like to slightly break a protocol and take the opportunity to felicitate Mr. Abid Das for his meticulous planning and dedicated efforts in organizing this event, right from the conceptualization to completion. I request Deepak Bhai to please present a Tulsi plant to.
What is the future of India? कैन ही कल है कल क्या है तो कैन ही कल है chemical engineering is the future of India. So welcome.
With few words I complete. I would also like to place on record my sincere appreciation to my back office team who have worked wonderfully behind the scenes to make this program possible. My heartfelt thanks to each one of them. I know that all of you are here with great interest to listen to our chief guest and eminent speakers and to gain valuable insights from their experience and expertise. So, without taking much of a time, I request Mr. Abid Das to take the program forward. Once again, a very warm welcome and big thank you to everyone for being with us today. Thank you, and I wish you all a fruitful and enriching workshop. Thank you.
Okay, yes, so we'll start the program with Sir B.N. Bangapurkar, and Sir has been the former director of IOCL, more than 50 years of experience in oil and gas. That's a lot. And he has led the Panipat naphtha cracker and Paradip refinery mega projects. Okay, so we take this opportunity to welcome Sir, and Sir will share his thoughts and start the session. Sir, please.
Good morning to all of you. I think it has been a wonderful experience for me to be back with the chemical engineers group here. And Mr. Kiyur Thakurji, Chairman, the Institute of Engineers, Vadodara branch, and other speakers of the day today, and my dear budding chemical engineers, as was said earlier, I think I'm happy to see that quite few young engineers around here. And ladies and gentlemen, I think it has been a very wonderful experience for me, and I feel extremely proud and happy to be here with all of you on a subject which is, I think, very apt and relevant in today's challenging world for the chemical industry. As you all know, chemical industry is a great contributor to the development of the country. And as earlier said, this contributes almost 1.4% or 1.5% to the GDP of 7%. So you can imagine the importance of chemical engineering and chemical industry in the growth of the country. And also, this is the sixth largest chemical producers in the world. So there is a kudos to the chemical engineering people who have relentlessly worked and tried to build up this industry for the benefit of the humankind and for the comforts of the people. Now, chemical engineering as today's topic, I think, is very apt, as I said, emerging trends. Today, industry is crossroads, having huge challenges on various activities. And certainly, one needs to look at how we can overcome the challenges. Has done wonderful work in the past, and it also, I'm sure, will be able to do that. But certainly, there's a need to stop and see where we are and what we need to do and what are the challenges. I think from that point of view, inputs which are going to come in this seminar are going to be very useful for the people, not only for the budding engineers, also for the experts who would always want to do something in the for the industry. The chemical industry is not simple like fabrication where you say every industry, every fabrication unit will do the same job. Here, I think chemical industry is an entirely diversified activity. It starts from refinery, petrochemicals, fertilizers. Then we have a heavy chemicals, we have a basic chemicals, we have agrochemicals, we have a specialty chemicals, we have pharmaceuticals. I think there's no end to what we can think of. I think every field we have a chemical industry, and challenges for each of these industry would be different and unique, and therefore the task on the chemical engineers would really high because they have to do quite a bit of work or research or do technology developments. Secondly, the most of these industries are environmental concerns. As these chemical industries they're basically very energy intensive. The energy requirement for these industries is really high, and therefore they have to burn some fuels, which ultimately results in huge energy and huge environmental emissions and becomes a cause of concern. Secondly, most of the chemicals are also classified as hazardous chemicals, which brings in a sense of the concern for the safety, and one needs to be highly conscious of the safety requirements, both from technology point of view and from human working point of view. So apart from these challenges, now today people talk about optimization, cost control, and then ease of operation. So naturally there will be huge requirement in terms of optimization, bringing in new technologies so which are more efficient. Like for example, like they always quote how it works. Like I joined way back in Gujarat Refinery, Baroda, as a trainee engineer. That time we had a column having a bubble cap trace supplied by Russians then. And now if someone talks about the bubble cap trace, I think someone will laugh at it. So that was the technology available then, where the material balance or the physical separation used to be maybe 40%, 50% of efficiency. And today we have a structured packings, we have a different size, different materials of packing, which will enable us to go to 80 to 90% of it. So this is where the chemical engineers needs to work on how we can really improve our make the efficient working of the existing facilities. So it happens in the catalyst and chemicals. The conversion rates have to be higher. For example, if you are looking at a process unit where there is a tracking, like in FCC, catalytic unit like FCC, the hydrocarbons are cracked and to make lower molecules so that you get lighter products like naphtha, gas, LPG. And there, if you are in a hydrocracker, we are adding hydrogen to it so that we bring back the volume of the molecule. So in this process, naturally, if the conversion rates are high, for the same capacity unit, for the same hydrogen consumption, you can increase your production levels. So these are the things which I think going on, but unfortunately, this is all we import today. None of the technologies are indigenous in major way. That is a pity that after so many years of independence, so many years of working, still we depend on either European or US technologies rather than our own. And there is a resistance also in the industry to not to adopt, because the reason being in cost of the cap unit which you have to put is huge. So naturally nobody wants to take a risk of investing huge cost in order to commercialize a plant. But anyway, I'm happy to say in Paradip refinery, we as the Indian Oil took up a indigenous technology for FCC, and against with all the risks which were involved with that. And this technology was fantastically good compared to any of the world-class technologies where we said the LPG production, particularly ethane and propane, propylene and ethane production was so huge against a conventional yield of 10 or 12% of C3s, and this unit was given 22%. That was the indigenous technology, but nobody wanted to implement because the cost involved was very high. Cost involved is I think about 5,000 to 6,000 crores. But anyway, we are done, and I'm happy to share that that technology has been proven successful, and IOC is today trying to export this technology. I think we already done one in. So that is are the challenges which one needs to face, and I'm saying in a very big way, where the cost is high, but there are plenty of areas where we can work on in a lower scale at a lower cost. I think it's possible to do that. But however, you should keep in mind today that there are a couple of compelling reasons for us. One is the environment. We need to get over environmental issues because emission CO2 being the biggest emission creates a problem. But now today again there are technologies and people are intending to get into use of CO2 which is emitted through the stacks for use production of useful products like ethanol or even polyols. Again, I'm happy to quote again IOC's example where in Gujarat refinery itself they are converting this CO2 emitted from the stack into polyol. The unit has been already commissioned recently, I suppose about 6 months back in Dumart complex. So these are the developments which is happening, but the scale of it which is happening very low. I think we have full potential. I think our chemicals are nowhere less to anyone in the world in terms of their knowledge and expertise. I think this needs to be exploited, which I feel is missing. Second is the safety. I think safety is very important because it has a hazardous chemicals, it has a high temperatures, very high pressures, and corrosion in nature, poisonous in this one. So in many ways it is going to be very hazardous. And one is process safety, where technologies and the controls would help us to do that. But second is the human intervention. The human behavior has to be absolutely precise so that we don't bypass or do shortcuts. This is a challenge. I think how the new industry is going to take it forward needs to be worked out. Then there is a huge requirement to reduce the fuel fired in the refinery, which ultimately raises the CO2 emission in the atmosphere. Now the trend is to use renewable energy for their heat source. For example, the fire heaters where we burn gas or fuel can be replaced by the electrical heaters and the electricity produced by renewable energy like wind or solar. So can be done in the steam boiler. Steam can be avoided. Instead of steam, we use electricity. And this is picking up in some of the Western countries, particularly Europe. And there are a few instances of being done in India, but then it needs to be done. This would be a challenge for everyone, small or big companies, because if we can avoid the fuel burning, would be a great help to the mankind. Then third is the carbon capture. Of course, it's in a big scale to be done. The carbon capture and utilization and storage, which is being done. I believe that ONGC has done some work on that, but it is yet to take over. It has to be done in a very, vast way, in a major way. That it is only like a pilot project which has been done. Now, last is the digitization of the operations is very important. use of AI is important, and this would help us to optimize our operations, minimize the safety risks, and also in conversions of which I was talking, it can be done. Energy conservation can be optimized. Most of the things can be done if we have a good digitization and use of AI tools. So you need to look in your operations where all you can bring these tools so that it helps improve performance, it helps improve productivity. And since you are young and growing up and having a good potential, I think you should look at the nanotechnology. Nanotechnology would certainly help you to where we use acres of land, probably we can bring it down to few, instead of thousands of acres, we can bring it to few acres only. I think that could be the possibility, but very few research is done on this area. And there is one company in Singapore which I am aware, they talked about CDU being built in a hall room like this in a modular way. So if that really materializes, probably you look at the saving of the land, and emissions could also be minimized. It will be controlled or stored in some places. So these are the areas which I would broadly look as a challenges. And today's program, which I have gone through, I think covers most of it. And I'm happy to note that. And there are eminent speakers who are going to deliver on that. So I'm very happy, and this program is organized, and I wish this program a great success, and thank the organizers, the Institute of Engineers, for having done so. Also my sincere thanks to Mr. Kirti for inviting me and giving me this opportunity. Thank you very much. All the best.
Thank you so much, sir. I'll to just felicitate sir with certificate and a small Tulsi plant. Sir has seeded his ideas into our mind. One idea I got about the electrical furnace. He said to in factory, that is a great idea. I hope everybody will take his words of wisdom. Deepak sir, please. Momentum. Our honorary secretary, sir, Deepak sir.
He's having an experience of more than 50 years. Your parents' age must be less than 50 years. So he has more experience than the age of sir. Thank you very much for accepting that.
So sir has enlightened us with his wisdom, and this has set the tone for the day. And yes, saving and optimizing energy is one of the key things he has talked about. And the chemical industry, which is having large factories, so each unit we optimize, we save a lot of fossil fuels being burnt, and that would save the earth, and that goes in the direction of sustainability. So optimization is not only reduces your cost and it improves the efficiency, but it actually goes into the sustainable development of the country. So we'll start the session with our first speaker, sir, Mr. UV Yagnik, and I have the privilege of working with him in GSFC Limited. He is currently the Vice President in the design department, and he has been designing all the aspects of the factory. So, and he is also our energy manager. So, how to optimize energy, if you have to learn, he is the best person to answer. And I guess his presentation will enlighten you, and definitely you will get good advantage.
Good morning, sir. Good morning, ladies and gentlemen. Good morning to all the students of the very chemical engineers. Before I start lecture, I would like to convey that GSFC was the first and pioneer industry, fertilizer industry, to diversify towards renewable energy, and we installed around 152 megawatt windmills in the span of 5 years from 2010 to 2015 at cost of around rupees 700 crores. And thereafter we have installed 65 megawatt of solar power plant, which includes 1 megawatt floating solar plant also. And we are planning to have another 30 megawatt solar power plant, as a result of which we are going to have 65% of our power through renewable energy. And as I conveyed to Dherasari sir just now, that because of very good integration of the steam network, at present, since last 4.5 months, we have stopped boilers and we are producing 200 metric ton per hour of steam, which is getting consumed in the various plants, and we are not consuming any natural gas.
घनश्याम भाई
So,
पहला लाइट बंद कराओ.
So this is good work done by GSFC, is a teamwork, and stoppage of boiler operation is still, I would consider, as a under experimental stage, but which appears to be very applicable.
Waste heat treatment.
Generated from our ammonia plants, sulfuric acid plants, and other plants.
Waste heat trigger.
Waste steam generated from other plants, ammonia and sulfuric acid plants.
પેલું આપો ને છે તો પછી એ બી છે કોલરમાં એક જ છે.
There are around 74
Color one?
slides, and I would like to slightly move fast. And you don't focus on the actual technological part, but the concept of power conservation considered for the various pumping systems. Energy conservation is the quickest, cheapest, and the most practical method of overcoming energy shortages. Energy is a manageable expense, and it can be easily controlled through dedicated efforts. So this should be our motto. An aspect of energy conservation is covered under ISO 9002 policy declared by GSFC. There was technical services department who carries out study related to energy conservation measures and work out basic scheme, and design department implements it by carrying out necessary design. Now since last 10 years, the services and design department are merged, but the basic functions have remained same. On implementation of measure, audit is also carried out by third party or by energy auditor, which is energy audit taking place at every 3 years. Energy manager governs all activities pertaining to energy conservation and remains in touch with Bureau of Energy Efficiency. And GSFC was the first industry to implement energy management system, British standard EN 16001, which got later on converted into ISO 50001. So first we will understand the elements of life cycle cost. The life cycle cost of the pumping this is the initial cost, this equipment, system, engineering, weed process cost, etc. to have weed for pumping. Then installation and commissioning cost. It is a foundation setting up to performance evaluation cost. Third is the energy cost, that is dominated on, and it is life cycle cost if it is more than 2,000 hours per year. And most of the plants are now running on continuous basis for more than 6,000 hours, so it is a basic governing cost. Then it comes operation cost, labor cost. With respect to the duty and complexity of the pumping system, it generates operating cost. Then maintenance cost and repair cost. It depends on time and frequency of service and the cost of materials. It depends also on the which chemicals it is being handled, like corrosive or some other cryogenic fluid, etc. Then downtime and loss production, that is may be optimized by using suitable number of standby pumps, so your plant doesn't have downtime. Then environment cost, it varies due to nature of the pumping product. In GSFC, we were also using hydrogen cyanide previously, so the what care requires to be taken to pump hydrogen cyanide is also very important. And then lastly, it is a disposal cost. Then it is applicable in case of hazardous or nuclear radiation area. As I conveyed, that pumps which are supplying hydrogen cyanide like hazardous chemicals. So these kind of pumps need special care while disposing of. So this is the ultimately life cycle cost of the entire pumping system. So in terms of cost, you consider that initial cost, there is a purchase cost and installation cost, etc. is only 2.5%. Maintenance, depending upon the pumping system, it is 10%. Others, there is miscellaneous cost, the disposal cost, and other cost is 2.5%, but energy cost is 85%. So in terms of graphical system, we can say that it is a initial cost is just the tip of the iceberg, but the main maintenance cost and energy cost are the main governing cost. So pumping system accounts for nearly 20% of world's electricity demand and range from 20 to 50% of energy usage in certain industrial plant operations. Like say suppose nylon 6 plant, which is small and which is not having much capacity, but the pumping cost in pump involvement in the processing is high, so it will have more amount of contribution towards pumping system. Basic principles of pumping are often misunderstood. It also contributes to the pumping cost. Running pumps delivering sufficient water or process fluid are considered to be functioning satisfactory. Means you are getting 1000 meter cube per hour of cooling water and supplied to the plant for cooling requirement. So means that the plant pump is running properly, but the performance is never measured. Production concerns outweigh pumping consideration. Production concerns outweigh pumping consideration means the aim of chemical engineer, the production department is focused entirely on the production only, that it should not get interrupted. Management also give more priority to that, and so the pumping related problems are overlooked. Then another is the lack of awareness of pumping cost. Management or any department doesn't provide sufficient education to engineers who join the industry and what are the pumping cost or the good factors contribute to the pumping cost. The life cycle costs are rarely considered at design stage. Nobody gives attention to the delivery period. Say suppose one pump is installed for energy conservation and one party is giving pump after 6 months and another party is giving up within 3 months. Then 3 months should be considered, and that because it is attributing to the energy conservation. Use of obsolete models are also one of the factors. Plants are running, like in GSFC, some of the pumps are running since last 50 years without having any proper thorough checking. So significant portion of cumulative electricity capacity addition of 19,000 megawatt can be avoided if pumping cost reduces. Now I would like to show some pictures which can be considered basic design flow. See, this pump suction is having bend in the suction line. It is not proper. The pump must have straight line with minimum number of bends as shown in this picture. So one should avoid bends in suction line to have minimum pressure drop across it. Another is this, you see this line is inclined. The structure is arranged in such a way that line is inclined, and which can contribute to the heavy vapor accumulation inside this, and it can also result into cavitation. This is another example in sulfuric acid plant that line is having bend. So bend should not be this, and line should be straight as indicated in this tank. The benzene coming from the tank to pump, it is having straight line. The same photograph, but it is indicated once again because the nozzle taken from the tank, it is having absolutely different orientation. Because of that, bend is required to be provided. So care is to be taken during designing stage that the nozzle orientation is absolutely in line with the pump location. So this is the pump area, and where the line nozzle taken was from different location. So the main reasons for higher specific consumption as per in Indian industry, as per the findings of BER, one is obsolete technology, lower capacity utilization, casual metering and monitoring of energy consumption, lower automation, poor raw material quality, poor handling, operating and maintenance practices. Now I will start various case studies implemented in GSFC. First case study is of Caprolactam 1 plant. As I said, you don't bother about the name of plant and products and etc. Just focus on the concept. The pump efficiency as per BEE may degrade between 10 to 25% in its lifetime. So average pumping efficiency in manufacturing plants can be less than 40%, with 10% of pump operating below 10% efficiency. We have seen some certain pumps specifically for low volume and high pressure, the pump efficiency is quite low. Cooling water pumps in this plant was running since commissioning of the plant in 1974, and when the energy audit was carried out, we found that energy efficiency was only 55%. So new set of pumps installed having higher head capacity and better efficiency. This is a pictorial diagram of this. These pumps were supplying 5,800 meter cube per hour of cooling water to various exchangers. And to allocate cooling water to the exchangers at higher location, booster pumps were also operated. So total power consumption was around 980 kilowatt. So this pump was replaced with pump having higher efficiency. And to meet the plant requirement at later stage, flow was increased from 5,800 to 6,800, and head was also increased from 35 to 40 meter. As a result of which we could stop running off booster pump. So the total power consumption with 5,800 meter cube was around 980 kilowatt, but with modification and with higher capacity, higher power consumption increased. But in terms of power consumption per meter cube, specific consumption of power per meter cube decreased from 0.169 to 0.146. So this is, and it could be possible to meet plant requirement running at 110% load. This is a pictorial diagram, this is a photograph of the new pumps installed in Caprolactam 1 plant. Similarly, in Meramine 1 plant also, where the new cooling water pump was installed in place of old pump operating at 55 to 60% efficiency with 82% efficiency. So the crux is that use energy efficient pumps. Nowadays cooling water pumps which are used widely are having 90%, more than 90% efficiency are available in the market. So one should install pump having very high efficiency. This is the same way that supply of cooling water as per location. In newer projects, this kind of approach are adopted. Suppose cooling water pump is supplying 6,800 meter cube of cooling water to all consumers located ground floor to 24 meter location, and this is the consumption rate and according to the elevation level. Now as you can see that much higher amount of cooling water, that is around 3,000 meter cube per hour, is supplied to elevation at 18 and 24 meter. Rest is at ground floor or below high level. So if the pump is, two pumps are installed, one pump which supplies more cooling water at higher head, it can be separately provided, and the another pump which is having low head, low volume, high volume product can also be segregated. So in this way also power saving can be realized. As per the calculation, this with flow of 3,800 meter cube and 20 meter head, power consumption is 277 kilowatt, and with 3,000 meter cube which is having 40 meter head, we will have 438. So total power consumption is 715 in place of 990 kilowatt. So where the plant is having high rise structure, like say suppose in our nylon 6 plant, plant is up to 30 meter height. So when only few consumers are there at top elevation, whereas the rest of the major consumer like VHP, which is supplying chilled water, is located at ground level, which is consuming major part of cooling water. So there should be two pumps. The one pump, common pump, should not have the maximum head to supply cooling water up to the high head, but it should be there should be small capacity high head pump, and the higher capacity and small head pump should be differently. So avoid generation of high head for bulk quantity. Supply cooling water as per floor wise requirement, provided less quantity is required at higher elevation. Now another thing, very common thing is use of low pressure drop NRV. Cooling water circulation of 20,000 meter cube per hour was required to operate our ammonia 4 plant. It was met by running 2 pumps. It was observed that pressure drop offered by NRV in pump discharge was sufficiently high. So NRV was replaced with low pressure drop, and it could increase pressure drop in the circuit, and thereby we could supply 1000 meter cube per hour more flow, which was essential to have a more to achieve more capacity of the plant. So these were the conventional NRV installed in this. In place of that, this wafer type check valve, swing check valve was installed, because of which we could supply power cooling water of 1000 meter cube per hour with same power rating. This is also the small use of wafer type NRV in condensate pump. So it is advisable to use NRV having minimum pressure drop across it. Now optimization of pumping system. In Caprolactam 2 plant, oxime and oleum are reacted to produce lactam. This is a highly exothermic reaction, and around 925 meter cube per hour of condensate was supplied by 2 number of pumps, which were consuming 144 kilowatt. So in place of that, when we checked, the flow requirement was only 740 meter cube per hour. So 1 pump of 740 meter cube was provided, and in that impeller diameter was increased. Generally we trim the impeller, which is a normal case. In this we increased impeller diameter in 1 pump, and we could achieve more capacity through that pump, and the overall power consumption could be reduced. So because there are 2 pumps were consuming 144 kilowatt, whereas 1 big higher capacity impeller consumed only 88 kilowatt, but still met the plant requirement. So this way also power saving can be realized. Then installation of higher size impeller by this. This is the blue colored this pump is the new pump installed. Then optimization of pumping system. You see in the plant when the plant operates for some years, there are certain changes taking place based on the technology, based on the steam and power balance of the entire complex, etc. So the original system does not remain valid or appropriate. So at that time, you need to revise the pumping methodology. As shown in the picture, based on the steam and power balance of entire complex, GSFC complex, STG3, which was the Am I audible? Should I continue?
Yeah, continue.
Yeah.
So STG3, which was generating 15 megawatt power, was stopped, and that's why the 500 meter cube per hour cooling water required. 500 meter cooling water required for STG3 was not. So in place of that, we stopped that, and we CCWP, that was 6,500 meter cube per hour supplied for condensation of steam, was also stopped. So the CWP, which was having 1000 meter cube per hour margin, was used to supply 400 meter cube per hour to cogeneration 1 plant, because the margin of 500 meter cube which was supplied from CWP to STG3 was not required. So 500 meter cube margin was available in CWP, and from that 400 meter cube per hour was supplied to cogeneration phase 1 and 2, and CWP 1 pump was stopped. Was stopped, and the full potential of CWP was utilized, which resulted into power saving. So one should look into the margin available in the 1 pump, and because of the change in the system based on the change in the operating practices, sometimes margin can be utilized elsewhere also. So use common pump as well as margin available in the system rather than running new and dedicated pump. This is the trimming of impeller. It is one of the most basic concept of power saving in pump, as shown in the plant in the slide. This is the ammonia 4 plant. Liquid ammonia is supplied to MP flat drum, then from MP to LP flat drum, and then vapor ammonia is supplied to refrigerant compressor. By operating
around 56 metric ton per hour to liquid ammonia storage tank. But based on the plant operation methodology, we started supplying hydrogen to various plants, synthesis gas to caprolactam 1 and caprolactam 2 plant, and ammonia at high pressure to urea plant. So the loading on T601 is reduced from 56 meter cube per hour to only 10 meter cube per hour. And because of that, the valve opening was only 5%. When you see that valve opening is much low, then at that time it indicates there is a potential of impeller trimming. So the impeller was trimmed and power conservation could be achieved by around 7 kilowatt hour. And the payback period was only 7 days. One of the most appreciable thing with the impeller trimming is that it is very simple and small, but definitely power saving can be realized through this technique. So this is the ammonia transfer pump, and these are the basic affinity law that when you trim the impeller, flow will change with the ratio of diameter, and pressure will change with the square of the ratio of diameter, and pressure will change with respect to power 3 to the diameter ratio of diameters. Another thing, we could save power in liquid ammonia transfer pump, that when this pump was designed to supply ammonia at maximum capacity, that is the plant capacity, motor was installed was of 42 kilowatts. But when the impeller was trimmed and pump was supplying only 10 meter cube per hour in place of 56 metric ton per hour, there was margin in motor also. So motor was replaced from 42 kilowatt to 23 kilowatt. Now any motor will operate, it will consume its no load current. So no load current, which refers to 42 kilowatt, is much more than no load current of 23 kilowatt. So by changing motor also from 42 to 23 kilowatt, we could save another 2.5 kilowatt. So this is also one of the way by which you can reduce your power consumption with impeller trimming. This is the case study of changing this operational control as shown in the slide. Condensate is received from third and fourth stage injector, and it is through barometric condenser, it is cooled and supplied to holding vessel. From holding vessel, it is supplied to at rate of 68 meter cube per hour to cooling tower. Now, because of the very less capacity of holding vessel, this pump was running in on and off condition. It was resulting into a lot of wear and tear in the pump, and so we supplied to the gravity line to cooling tower. So, and this pump could be stopped. So, because this barometric condenser was located at 6.5 meter elevation and cooling tower basin was around 3.2 meter height, gravity transfer was possible. So, by supplying through gravity, we could stop the pump and we could save the power. So, I'm sorry. I'm sorry.
You can break for tea and then.
No, I just completely forgot that I am seeing but you are not seeing. I'm so sorry. I thought that I.
No, it's okay. So we can break for tea first, start by the power supply is restored, then we can. Yeah, that's good.